Okay, in the previous lecture, we developed the idea of the Rayleigh-Ritz method or the Ritz method. And I said the next lecture would be on linking that to finite element analysis, which is sort of the goal of this whole course. So I want to do that here today, try to bring everything full circle and show you what we can learn from a variational approach to FEA. So let me remind you that we'd shown that the total potential energy for an elastic body was as follows. So we had that the total potential energy pi was equal to 1/2 times the integral over the volume of epsilon ij, epsilon kl, Cij kl dV minus integral over the volume of Bi ui dV minus the integral over the traction surface Ti ui ds. Okay, let's call that equation 1. All right, I'm going to now switch from our index tensor notation back to Voigt notation because it's more convenient in this case. So let's rewrite equation 1 using Voigt notation. So here we'll say pi is equal to 1/2 integral over the volume, except now instead of this epsilon ij term, we're going to have the strain vector. We'll call it epsilon transpose times the stiffness matrix C, which is 6 by 6, times epsilon, okay, dV, right, minus the integral over the volume of B transpose times U dV minus the integral over the traction surface of T transpose times U ds. So let's call that equation 2. And I'll just remind you what this new epsilon vector looks like. So where epsilon transpose is equal to epsilon 1,1, epsilon 2,2, epsilon 3,3, gamma 1,2, gamma 1,3, gamma 2,3. Okay, so we'll call that equation 3 just as a definition. So now what I'm going to do is I'm going to basically divide the domain of whatever this elastic body is up into elements, and I'm going to break this integral up into a sum over the elements. Okay, so what we'll have then is pi, and I'll still have my my 1/2 here. So what I want to do now is to break this integral up as a sum over all the elements. So I still have I'll have a summation going from I equals 1 to n, where n is the number of elements. And we'll say this is integral now over the volume of the ith element times this quantity epsilon transpose times C times epsilon and then dVi, right? So as we're integrating over this volume, minus the same thing here now. This will be the sum from I equals 1 to n of the integral now over Vi of B transpose times U times dV minus the sum from I equals 1 to n of the integral over the traction surface of that particular element, if it has one. Now T transpose times U ds. We'll call that equation 4. Okay, so now it's in a form, we're going to use the Rayleigh-Ritz method as we described earlier, except we're going to make 2 changes. Okay, so change number 1. Instead of solving for a single complicated function over the domain, we're going to choose an approximate function that's piecewise continuous across the domain. And that function is also going to be continuous within each element. Okay, let's jump to the second change we're going to make. We're going to replace, so number 2, we're going to replace the generic constants that we used, like C1, C2, and C3 that we tried to solve for earlier. Okay, we're going to replace those with the nodal degrees of freedom of our elements. So in this case, that would be something like, let's say, instead of C1, C2, etc., now we're going to have U1, V1, W1, those are our X, Y, and Z displacements, U2, V2, W2, right, etc. Okay? You've seen this before. This is what we have already done many times in our intro to FEA course, was showed how we can do that, how we basically take our undetermined coefficients and we now make the nodal quantities those undetermined coefficients, okay? So this results in our sort of traditional approximation function. So for example, if we introduce again our interpolation functions n, and we could then write that, let's say, u star, right? This would be the approximation of u would be equal to n transpose, right, which is our interpolation function vector, times ue, right? In this case, this will be our, these are our nodal displacements. Okay, we'll call this equation 5. So this is hopefully should be very familiar to you now. Okay, so we want to use the equation 5 in equation 4, but it's not, we haven't really done a lot with Voigt notation, so I need to just briefly tell you how we're going to link equation 5 to equation 4. So in Voigt notation, the equation between strain and displacement is given as follows. Right, we would say that the strain is going to be equal to some differential operator matrix that we'll call del, okay, times u, and in this case u is not just x here. What I really mean by u is that it's going to be the UVW components of displacement. So we could write this as u, v, and w. Okay, so that's how we define strain. Let's call that equation 6. So what does this del matrix look like, this differential operator matrix? Well, it looks as follows. Okay, so we know that we got to take a 3 vector and move it to a 6 vector. So this has to be 6 by 3. So that first row is just del by del x, 0, 0, and then 0 del by del y, 0. The next row is 0, 0, del by del z, right? Next row is going to be del by del y, del by del x, 0. Next row is going to be 0 in the middle, del by del z, del by del x, and then that last row is going to be 0 and then del by del z, del by del y. Okay? So we'll call this equation 7. You can go back if you need to and convince yourself that that's the case, but that gives us the small strain approximation that we've talked about previously. Okay, so per equation 5 then we can write the following. So what we want to say is, well, what is this UVW term? And since equation 5 describes how UV and W are approximated, we could write this as a column vector here. So this is N transpose. Okay, and I realize being a little sloppy here, but this will just be UE. Okay, so this will be N transpose times VE. These are the element nodal displacements, and then this third term is N transpose times WE. Okay, and this whole thing is a vector, of course. Okay, so we could rewrite this then as some matrix N times this vector that looks like UE, VE WE. Okay, something like that. We're going to call this whole vector just DE. Okay, so we'll call this as N times DE. So whenever you see DE, think of these are all of our nodal degrees of freedom. Okay, so really I'm just introducing a bunch of definitions here so we can simplify our equations. Call that equation 8. So now let's substitute equation 8 into equation 6. And now we can get our relationship here between our strain term and our nodal degrees of freedom. So there's our del matrix now times our n, which is our interpolation function matrix, times our nodal degrees of freedom. Call that dE, right? So this would be at the element level. Let's call that equation 9. Now I'm going to further introduce some definitions. So I'm going to define what del operating on n is. And I'm going to define that as B, capital B, is going to be equal to del times n. Okay? I'll call that equation 10. So that I can write equation 9 as follows. We can say then that this is epsilon is equal to B times our nodal degrees of freedom. Okay? Call that equation 11. Okay, so now I'm ready to do some substitution back into my function for potential energy. So I want to substitute equation 8 and equation 11 into that form for potential energy given by equation 4. When I do that, I end up with pi is equal to 1/2 times the sum from I equals 1 to n of the integral now over VI, okay, times dE transpose, and that's of course for the ith element, times B transpose times whatever the stiffness matrix is, C for the ith element, times B times DI, DEI rather. Okay, dV, so that's the first term, minus the sum from I equals 1 to n, now of the integral over VI, and this term is little b transpose I for that element, times n times dEI, dV, and then our final term is a minus the sum from I equals 1 to n, integral over now SI of the traction portion of that, times the traction of the ith element, n dEI ds. Okay, call this equation 12. Okay, so kind of a long and nasty equation. So we're going to introduce the following definitions. Okay, we're going to define what amounts to an element stiffness matrix. We'll call it Ke sub I. It's going to be equal to the integral over the element volume of B transpose times C I times B dV. Okay, so and why can I do that? Because these D terms are just nodal coefficients, right? They're not functions of, they're not functions, so I can pull them outside the integral. Okay, so I'm going to call this equation 13. And then I'm also going to define this something I'll call Ri, okay, which is similar to what we've talked about before. So this becomes integral VI now times BI transpose times N. And I shouldn't mention this must be a transpose, dV. And then I can say this is plus, now the integral over SIT of TI transpose times N ds. Let's call that equation 14. So I can now substitute 13 and 14 into 12 and write the following. So we have pi now is equal to 1/2 times the sum from I equals 1 to n of d e I transpose times now our element stiffness matrix k e I times d e I. Okay, so that's the first term. How about the second term? Now this just becomes the sum from I equals 1 to n. We actually took a transpose of both sides to do this so that we end up with similar looking terms. dE I transpose now times RE I. Okay? So that's equation 15. Okay, so what do we want to observe? We want to observe that in equation 15, we basically have the summation of our elements in terms of strain energy and the boundary and body force terms, right? That's what this represents. Okay, so we're getting close to moving this so where we can say we've completed the Ritz method. What we need to do now is we want to put this all into a global system to try to, as best we can, remove the summation so that we can go ahead and try to extremize this potential and see what we get. Okay, so let's go ahead and consider the mapping from the global degrees of freedom to the local degrees of freedom. And so we would write that as, so we have dE I is going to be equal to some mapping, we'll call it L, which will be unique to the element, times this global degree of freedom vector that we'll just call D, capital D. Okay, so this is our local degree of freedom. This D is our global degree of freedom. And this L, this is just a Boolean matrix that maps global to local. Okay, we'll call this equation 16. I will say that when we actually code this up, we don't usually use something like L, but it helps for developing the theory. We probably have quicker ways to assemble a global stiffness matrix and assemble the degrees of freedom than having to write out something as large as L for each element, okay? So now we'll substitute 16 into 15. Okay, and when we do that, we end up with pi is equal to 1/2 now times D transpose, and then I'm gonna put deliberately some parentheses to separate this out. The sum from I equals 1 to n of L I transpose times K element stiffness matrix E of element I times L I, close parentheses, times D. Okay? So that's the first term when we make that substitution. And then I'm going to say minus, I'm going to pull out now another D transpose out of there, times the sum from I equals 1 to n, Li transpose times REI. Right? Let's call that equation 17. So what I want to do now is I want to define the global stiffness matrix K as follows. I want to say, let's let K be equal to the sum from I equals 1 to n of Li transpose times KEI times Li. Okay, and we'll call that equation 18. I want to define the force vector as follows, right? Or it's also sometimes called the reaction vector. We'll call it capital R, right? We'll define that as the sum from I equals 1 to n of Li transpose times REI I. Let's call that equation 19. Okay, what I can do now is I can substitute equations 18 and 19 into 17. And I end up with pi, the total potential energy of the system, is equal to 1/2 d transpose times the global stiffness matrix K times d minus d transpose times R. Okay, call that equation 20. Okay, so what have I done? We have, via the Ritz method, we've converted the functional, which was pi as a function of u, the displacement, into a function, which is now pi as a function of the nodal displacement vector d. And so now we know how to handle this. We can extremize the function by taking the following. All right, we would say that del pi, now del with respect to our variables, our vector now d, equals 0, right? Let's call that equation 21. So what does that look like? I want to apply equation 21 to equation 20. So when we do that, we end up with that delta pi, or del pi del d, rather, is going to be equal to that first term. It's just going to become, that's effectively 1/2 kd squared. So if we take that derivative, it just becomes kd. Okay, and then the second term becomes just minus r. And that's going to be equal to 0, right, which we can rearrange such that we have k times d equals r. Let's call that equation 22. Okay, so what did we just do? We just arrived at the classic linear elastic finite element matrix equations that we have to solve. We have kd equals r. We've written it before as ku equals r. But this time we did it by minimizing the total potential energy of the system. Okay, so that gives us an important corollary. Okay, so here's our observation. That the governing equations of FEA arise from the minimization, or the minimization of the total potential energy of the system. Okay, and you have when you first started solving these equations, at least the way that I've taught it in the past, what we typically have done was take the equations of motion, put them into a weak form, introduce something like the Galerkin method and solved, and we got a solution. What I'm showing you here was that same solution is actually the solution that also minimizes the total potential energy. So there is a linkage there that's important to know. And we could also begin the whole analysis just by knowing the total potential energy and get to our equations from that by minimizing that using this Ritz method.